Chuck, do you hear us? Can you hear us? Hello?
Yeah, I hear you.
Yeah, okay.
Boris.
Boris, do you hear us?
Yes, I hear you.
Very good, thanks. Okay, great. So then,
Then
now
I just share my screen.
So you share your screen, yes.
I share my screen. Share.
Perfect. It's all done?
Yeah, I think then we're all set. Okay. Just do full screen.
Yeah, perfect. Perfect. Okay, great. Thanks very much for coming. Special seminar always requires special attention. It's a really great pleasure to welcome Erez Berg, who is a great friend of Minnesota. He's been here many times, experiencing wonderful cold that we brought us snow. Actually 2 days ago. So Erez got his master in Technion, working with Erez Berg, then crossed the pond and went to Stanford, where he was a graduate student with Steve Kivelson. After that, he moved to Princeton, also to Harvard, where he was a postdoc with Subir Sajdov and Eugene Demler. And then he got a professor position in Weizmann, where he been since that, except for a 1-year tour to Chicago and back, just to see how windy city can be terrible at bad times. So Erez worked on all subjects that people here work. We all happily collaborate with him, have papers with a number of us, which is absolutely great. And today he's going to talk about what the Wiedemann-Franz law tells us about strange metals. And welcome.
Yeah, thank you
You
very
know
much.
to interrupt.
Yeah, of course. Yeah, please interrupt. It's always wonderful to be back here. I apologize for bringing the winter with me, but you have to understand. I mean, for me, seeing snow is really exciting, so I couldn't miss out on the opportunity. So I hope you understand. So I'm going to talk about various projects all surrounding this. Thank you. This issue of the Wiedemann-Franz law and what it can tell us about various non-Fermi liquid metals. I'll mention work done with various people, which I'll highlight as I go along. Okay, so just as a background, what we're trying to do is to understand various strongly correlated metallic systems that seem to not be well described by Fermi liquid theory. And there are many examples of that. I think there's quite little understanding, and we want to try to use information from thermal conductivity to get a hint of what's going on. Okay, the strategy in this talk would be to sort of start from the least strange metals, so something that we think we do understand, and it's deviates from liquid theory, but very gently, and try to see what we can understand there. And we'll discuss the Wiedemann-Franz law and how it can break down and what it can actually tell us. And then gradually we'll move up in the level of strangeness to the really weird systems like cuprates, systems that show linear interior resistivity down to extremely low temperatures, which is one of the big mysteries of the field. And we don't have a theory for what's going on there, but we propose that examining the Wiedemann-Franz law or the Lorenz ratio in these systems can actually give us some very valuable information about what is actually going on. Okay, so that's our strategy. So we'll start from not so strange metals, and that is strontium glutamate 214. Okay, so this is a textbook Fermi liquid, but it turns out that it can be tuned in a very interesting way. It can actually be tuned by strain to the Van Hove singularity. Okay, so this was done by Clifford Hicks and company. Okay, so it turns out that at zero strain, these are the different Fermi surfaces. This is a multi-band system. And one of these bands, so-called gamma band, one in blue here, is naturally very close to the zone edge. And it just needs a little bit of push, a little bit of pressure, and in this case, uniaxial pressure. And you can really tune it beautifully through the Van Hoff singularity, where this Fermi surface reconnects and changes its topology. And the question I'll be asking here is, well, what happens to transport properties as you cross this Van Hoff singularity? Now, my initial intuition would have been, if you asked me before 2018, would be that nothing should happen to transport, because you're really just modifying the dispersion drastically only close to this one point. The Fermi velocity is going to 0 at that one point, but you would think that it's, this one point is sort of shortened by all the rest of the Fermi surface. So this should not be visible in transport, but it turns out that this is actually not what happens. Okay, so this is a plot of the logarithmic derivative of the resistivity.
Erez.
Yeah.
We don't see moving slides. We are sitting on the first slide yet.
Oh, so the title here should be turning through the Van Hoff singularity.
I repeat, we see only first slide with your name, nothing else.
So let me try to stop the sharing and share again. Yeah. Let me try this. Okay. Sorry about that.
Okay, this is better. Now we see Van Hoff slide.
Yeah. Okay. So then I'll try
Did
to.
we miss the other one, or it's number 3?
Yeah.
Show us number 2, please.
Yeah. This is okay. Sorry. This is number 2. Let me try to run the slideshow again. Let's see if it's updating now. What do you see now, Boris?
I outline.
Outline, great.
Outline. Okay. Also, you can increase the size.
Yeah. Right. Let's see. And now is it? Did it go to the next slide?
No, I still see outline.
Let me. Oh, okay. Okay. Yeah. Let me try that. So I'll just share the entire screen. Share desktop. Yeah. Okay. All right. So and now let's try to go into slideshow.
Okay.
Yeah. Now is it changing when I click?
This is slide 2. Everything is changing.
Yeah.
You can go ahead.
Okay. Right. All right. So this is a plot of the logarithmic derivative of the resistivity as a function of temperature and strain. Okay, and this is where the Van Hoff singularity is believed to be, and you see that on both sides it kind of approaches this blue color, which is t². This is what you expect in a Fermi liquid, but you see this kind of fan-shaped region where it becomes yellow. This logarithmic derivative maybe approaches 1.5. Okay, so something clearly dramatic is going on in the resistivity. If you just plot the resistivity itself, there would be a big peak around this Van Hoff value. And this is actually a plot of the resistivity as a function of temperature right here, right where the Van Hoff singularity is believed to occur close to -0.6. Okay, and you see the curve here. It actually fits either t² log t or t to a power law, which the power is close to 1.5. And they now have actually more data to lower temperatures by suppressing superconductivity by a field. And it seems to be fitting better to t² log t.
Can you take the derivative? Let's see. This is what?
Yeah, so this is the derivative.
No. The first derivative you wrote in t. To see if I guess it is 1.5 and 2.
Yeah.
1 and 2.
Yeah. Right.
So does it mean that if you really try feeding, as many people do, or substantial temperature range, power 1.5 and t² log give you pretty much the same?
Yeah. So you can see it here. So this is from 3 Kelvin, which is TC, up to 40 Kelvin. And I don't know if you can see it. There are there's the experimental curve and 2 fits, 2 colors, blue and red. Okay, maybe it's hard to see. But
red dots, yeah.
Yeah. And they basically sit on the curve, smack on. You just can't distinguish. Now they've gone to lower temperature, and they're
What is the scale inside the water?
230.
yeah, yes,
Oh.
yeah, yeah. Right.
Is it odd that it's so large this big?
It's in a sense, for me, it was odd that it's so small. So if you think what the scale should be, naively, I would say Fermi energy.
Oh.
It's something like the effective mass. We need a theory to discuss what that scale is, and I'll show you a theory in a moment. Okay, so right, but this is the experimental observation. If you suppress superconductivity by a field, you can go to lower temperature, and T squared log T is visibly better. Okay. All right, so what is actually going on? Okay, so why is the Van 't Hoff singularity visible in transport at all? Why isn't the Van 't Hoff singularity short-circuited by some of the other portions of the Fermi surface? Okay, so to understand that, you need to think about the different scattering mechanisms that can happen on the Fermi surface when you tune to the Van 't Hoff singularity. Okay, so what we're doing is we're tuning one of the bands to the Van 't Hoff point. Okay, and you can have different scattering mechanisms. So let's imagine splitting our Fermi surface or our Fermi surfaces into different portions. There's the hot portions, which are some regions in the vicinity of the Van 't Hoff singularities, and the cold portions, which are everywhere else. So clearly, we can have a scattering process like this: two cold electrons, cold, going into cold, scattering into portions of the Fermi surface far away from the Van 't Hoff singularity. Then we can have this type of scattering process: two cold electrons scattering off each other. One of them is going from cold to cold, but the other one is going from cold to hot. Okay, basically scattering into the Van 't Hoff singularity. And finally, we can have a cold-hot, a pair of electrons, one at the Van 't Hoff singularity and the other one far away, and just scattering into a cold-hot. Okay, this scattering must involve a small momentum transfer, so the hot has to scatter back again into hot. It could scatter also into the other Van 't Hoff singularity. In this case, there's actually only one. These two are related by reciprocal lattice vector, but more generally, it can be another Van 't Hoff singularity. Okay, and now we can analyze the contribution to these different scattering processes to the resistivity. Okay, so the cold to cold would give us the usual T squared of a Fermi liquid. Now, the cold hot into cold hot can give us something which has a different scaling than Fermi liquid because of the fact that we have such a flat dispersion close to the Van 't Hoff singularity. But this is a very small angle scattering. It involves a very small momentum transfer. So this actually doesn't show up. It's there. It is very, very singular, but it doesn't show up in the electrical resistivity. Yes.
So if I start, just look at the center and let's say we fix the arrow on the upper left and rotate the entire picture by 180 degrees, do we have scattering? So
Yeah. So cold to hot. That can happen. Yes, yeah, that's a good question. That's actually not highlighted here. There's another type of scattering process where two cold electrons, say from here to here, and from here can both scatter into the hot. So cold to hot. That's also possible. Let me get back to that in a second. Okay, so yeah, excellent question. So, but let's focus for a second about on this type of scattering process. Okay, so a pair of cold electrons, one scattered into cold and the other one into hot. It turns out that if you have a complicated enough dispersion like you do in a sort of today, this can actually happen completely generically anywhere on the Fermi surface. So any cold electron can find another cold electron such that one of them scatters into cold and the other one into hot. So this scattering mechanism is active over the entire cold Fermi surface. And moreover, you see that this scattering mechanism generically is a large angle scattering. Okay, it involves a large momentum transfer and a large change in the velocity. So this would actually affect the resistivity strongly. Yes.
But you need more than one band for that.
Yes, it turns out that you need more than one band. Absolutely. Okay, so if you only have one band, you can still do this via Umklapp scattering.
Right.
But it turns out that at the lowest temperature, there's no phase space. There's some region of the cold Fermi surface that can't do this. So it's lucky for us that there are actually multiple bands.
So you avoid Umklapps, necessity of Umklapp because of many bands.
Yeah, so we need the umklapp also because you know, we don't want to have momentum conservation, but that's okay. This is large angle scattering. Umklapp is as likely as non-umklapp scattering.
But in the process that you show,
this is non-umklapp,
this
but
is
but
not
I could have drawn a similar umklapp process. So instead of scattering from here to here, I could have scattered from here to there, by the same momentum transfer, and that would scatter me to the next Bernoulli zone. Okay, so yeah. So I mean, it's important to have umklapps, but it's larger angle scattering. So generically, this is what you get. Okay, and just returning to the question about cold to hot scattering, that definitely can happen, but that's like scattering in the Cooper channel that generically can only happen for a pair of colds that have zero center of mass momentum. So they also have zero current. So this process actually doesn't enter resistivity. Okay, it doesn't modify the current of the scattering electrons. This is why we're not taking it into account here. It's important for other things, but not for resistivity. Okay, so bottom line, if you do the calculation, the scattering rate, the transport scattering rate you get out of this cold to cold hot gives you t squared log t. Okay, and the log is just coming from the log singularity of the density of states at the Van Hoff singularity. Okay, and let me just mention that if you get the stronger peak in the density of states, like a higher order Van Hoff singularity, you would get a different behavior. You might get a different power law. And in fact, we proposed in a related system, which is the bilayer starting with where the resistivity is linear, we propose that if you have a strong enough peak in the density of states, which is essentially delta function like, you might get this behavior, both resistivity that's going like t and specific heat that's going like t log t. Okay, but this is more speculative. Here we know what we're doing. We know that we are tuning to a Van Hoff singularity of this form. Yes.
I'm confused by one thing here. So if I compare this to the situation of scattering by interferomagnetic fluctuation, right,
yes,
where you have hotspots and
yes,
cold spots.
yes.
One of these stories, I mean, you haven't really told why this process is not short-circuited by CCC, right? Well, I remember that the story was that if you have enough disorder, right, the first correction is the linear t, and not the
this is not the case here.
But that's the opposite here, because t squared log t is higher.
Is higher, exactly. So the important thing is that this scattering event, that's crucial here, this scattering event can happen anywhere on the Fermi surface. Right. It's not on hotspots. It involves the hotspots in terms of Van Hoff, but you just scatter into those.
Sure.
Okay, so yeah.
It's the same question that Rafael asked. Maybe you can say in one word. What's the crucial difference with scattering by antiferromagnetic fluctuation?
So the crucial difference is that the scattering rate is singular only at one momentum transfer. So it can only happen at hotspots on the Fermi surface in 2D. Okay, here, this momentum change is not restricted to any particular value. You can, from anywhere on the cold Fermi surface, you can scatter into the Van Hoff singularity, and somewhere else on the cold Fermi surface, given that the cold Fermi surface is complicated enough, can take that momentum difference.
And if you do the same with scattering, that cold, hot, but hot will be hot spot.
Yeah. So then what you'll pick up is the density of states at the hotspot.
Right.
And then the question is, how singular is the density of states at the hotspot?
Mm-hmm.
Okay, and that's actually a very interesting question. Okay, so if the self energy at the antiferromagnetic critical point depends only on frequency and not on a momentum, the density of states is actually not singular. Right, there's a cancellation between the z and the mass, so you wouldn't actually get anything. You would need some other behavior. So it's a very good direction. We tried to go there. We have not gone far. Okay. All right. So this is what happens for the electrical resistivity in this problem. Okay, but what I'd like to point your attention to is that there are these cold hot to cold hot processes that are going on. They're actually much more singular. Okay, so their temperature dependence, as I'll show later, turns out to be a power law, not logarithmic. It's actually t to the 3/2. They're much bigger. These processes are much stronger at low temperature than this t squared log t, but they're just not showing up in the electrical resistivity because it's small angle scattering. The question is, where do they show up? And they do affect the thermal resistivity, because thermal resistivity, it does pick up also small angle scattering. So there would be something dramatic in the thermal conductivity going on here. Yes.
So does the scattering amplitude depends on the momentum transfer?
Yes. Yeah. Very strongly. Exactly.
So it does this select some momentum transfer?
Yeah. So you know, this there would be a special similar behavior for strictly speaking at zero temperature. Q equals 0. If you look at the function of frequency instead of temperature, at Q equals 0, momentum transfer is this special similarity, and it gets smoothed out if you move away.
Erez,
Yes.
please don't go too far from your computer, because
sorry.
you're losing voice
Yeah,
when
yeah.
you're going out. Okay.
Yeah. I'll just I'll try to stand here, and if I don't, remind me.
Yeah, at least not too
Can you,
far.
can you hear me?
Yes. When you're close, we hear you fantastic.
Okay.
Well,
right.
but yeah, please don't go away.
Yeah. All right.
To Chubukov.
Yeah. Okay. So we suspect that something interesting would be happening in the thermal conductivity close to the Van Hoff singularity. And for that, I'd like to just this is a reminder. Sorry about that. Just a quick recap of the Wiedemann-Franz law. Okay, so this is saying that if you look at the Lorenz ratio, which is the ratio between kappa, the thermal conductivity, to T times sigma. Sigma is the electrical conductivity. Okay, so in metals at low temperature, this should approach this universal value. Okay, and it's really a striking thing. So you know, there's very in condensed matter physics, there's not a lot we can say quantitatively about general systems, and this is really saying that this Lorenz ratio should approach a value which is basically pi squared over 3 times fundamental constants. That's it. This was pointed out phenomenologically already in 1853. Of course, they didn't talk about, they just observed this phenomenologically at room temperature, but it turns out that if you go to 0 temperature, this is the correct value. This was actually one of the first successes of the quantum theory of metals, predicting this value. Okay, and here just a flash of a few metallic systems showing this Lorenz ratio in units of L naught as a function of temperature. Okay, so this is nickel. Okay, so you see how it deviates from 1, but it approaches 1 in the limit of 0 temperature. This is a quasi-1D metal. This is silver. Okay, so you see this this nice convergence into 1, and this is actually a heavy fermion material. So even in heavy fermions at low temperature, in most systems, it actually approaches 1. Okay, and the reason that this holds is actually very, very simple. If you go to low enough temperature in a Fermi liquid, the scattering is elastic. Okay, and if you just think in terms of Boltzmann theory. Okay, so if you just write the expression for the electrical current and the thermal current within Boltzmann theory, you see that they both depend on the quasi-particle velocity and the density, and the thermal current also depends on the energy of the quasi-particles. But if the scattering is completely elastic, the only way you can degrade either the electrical or the thermal current is by degrading the quasi-particle velocity. When the quasi-particle scatters elastically, it changes its velocity, but it doesn't change its energy. So elastic scattering processes actually affect the electrical current and the thermal current exactly in the same way. Okay, this is the key element for the Wiedemann-Franz law. But this also tells you immediately that if you have inelastic scattering, strongly inelastic scattering, that can actually affect the thermal conductivity, the thermal current differently from the electrical current. And then you would expect to find a violation of the Wiedemann-Franz law. Okay, and this is actually what we expect in our system. So if we look at the metal close to a Van Hoff singularity, we have these small angle scattering processes that don't change the current a lot, the velocity a lot, these CH to CH processes, but they are strongly inelastic. So they should show up in the thermal conductivity, but not in the electrical conductivity. Okay, so this is the process we're talking about. It's the self-energy of the cold electron, shown in blue, as a result of scattering from the hot electrons. Okay, and if you do the calculation, okay, so you find this charge susceptibility of the hot electrons that follows this behavior at small q and small omega, and the corresponding cold electron self-energy actually goes like this. It's the maximum between t to the power 3/2 and omega to the power 3/2. Okay, so non-Fermi liquid, it's a power law. Okay, and this would actually affect directly the thermal conductivity, but not the electrical conductivity, which, as we saw, goes like 1 over t squared log t. The thermal conductivity over t goes like 1 over t to the 3/2. As a result, what you expect is a strong violation of the Wiedemann-Franz law as you go to low temperature. Okay, so if you just take the ratio, the Lorenz ratio should follow this behavior: square root of t times log of 1 over t. Yes.
But I mean, I agree with that, but once you get to very low temperatures, it's unavoidable that you only have elastic scatter, right?
Right.
So this violation that you're talking about is there has to be another temperature scale there where it just cuts off.
Yeah, absolutely. This is all these considerations are for a clean system,
Right.
Zero disorder. What would happen if you have a little bit of elastic scattering? Okay, so strontium ruthenate is extremely pure. Okay, so but if you add even a little bit of elastic scattering, what will happen is that these curves are the red one is exactly at the Van Hoek point. Okay, so it will start going down, but at temperature, which is of order of the elastic scattering rate, it will just recover and go back to 1.
But you always go to 1, no matter how
Always
small
go to
it
1.
is. The question is when.
At what temperature? Okay,
And also, I guess we can use the word non-Fermi liquid a couple of times. I think this Fermi liquid in the sense that quasi-particles are still propagating.
yes,
And obviously, otherwise you will not be able to do this calculation.
Well, okay, we'll get back to that. Okay, so I completely agree that in the Landau sense, this is still Fermi liquid. Okay, in the sense that the scattering rate of the electron at low energies is parametrically smaller than its energy.
And you do calculations with free fermions.
Boltzmann, yeah, essentially free fermions. That's the next question. Okay, so that's what we want to understand next. Okay, so this is our prediction for the system, a pronounced violation of the Wiedemann-Franz law. As Raphael pointed out, it should recover at low temperature. We'll discuss how it recovers, but it should go back to 1 eventually. Okay, and there are various other mechanisms that use the same effect. So whenever you have a forward scattering, which is strongly inelastic, you expect some sort of violation of the Wiedemann-Franz law. And there are various examples that have been pointed out. All right. Okay, so now we want to, having analyzed this example, we want to move to more interesting systems and see what the Lorenz ratio in these systems can tell us about the mechanism of scattering. Yeah.
1 second before you go to that.
Yeah.
What about experiments from strontium ruthenate?
Yeah, so the thermal conductivity at the Van Hoek point has not been done yet.
Must be hard, right? Because you need to have the strain cell, right?
Yeah, you have to do it under strain. Now, it doesn't have to be this uniaxial strain. You can tune to the Van Hoek singularity also using C-axis pressure, which maybe is a little bit easier. But sorry, yeah. But okay, but this experiment has not been done. Okay, so here's just one example of what we might learn from the temperature dependence of the Lorenz ratio about an apparently strange metal.
Erez, sorry.
Yeah.
You showed some pictures, right? That showed this recovery, right?
Yes. Yeah.
And I think in your calculation, the examples that you show, it always starts below and
Yes.
it goes up.
Yes. Yes.
Are there data where it goes above the limit?
There is data where it goes above. I've not seen data where it goes. It's sort of reaches 1 at the lowest temperatures, and then the first deviation is above. It's always below.
Right.
Okay, I don't think that's a theorem. I think that's. I'm not sure that's something fundamental, but that's true in all the examples I'll show, basically. Okay, in cuprates at finite temperatures, it does go above. Okay, so here's just flashing one more example. Okay, this is a telephosite metals. So there's palladium chromate that has this is actually layers of matte insulator would be which are sandwiched between the layers of an extremely good metal, and this is actually the magnetic transition of the antiferromagnetic layers. And there's this very broad regime of linear resistivity. It's been claimed that this linear resistivity is something unusual, cannot be just the usual phonon mechanism at high temperature. And the reason is comparing this, this compound with a sister compound that has chromium substituted by cobalt, which is non-magnetic. And you see that the resistivity is very different, both in magnitude and in the qualitative behavior. Here it's linear and here it's curving up. Okay, but a measurement of the Lorenz ratio by Mackenzie's group showed that the Lorenz ratio at low temperature is sort of approaching 1. At intermediate temperature, it does something more complicated. This is actually the magnetic transition. But you see that at high temperature, where the linear resistivity is, it actually approaches 1. Again, this is actually a hint of quasi-elastic scattering from phonons. If the scattering is quasi-elastic, this is exactly what you expect. So somehow the phonons are probably still responsible to this, for this linear in T. Okay, there's some puzzles, some other puzzles related to this material. What causes the difference then between the magnetic and non-magnetic compound? The scattering rate in the magnetic one seems to be basically KBT over H bar with the coefficient which is very close to 1. Okay, it's not good understanding of that, but it looks like it is quasi-elastic scattering. Okay, so now I'm going to move to the strangest of all. Okay, so cuprates. Here we know that in many cuprates, if you suppress superconductivity by a strong field and you measure the resistivity of the normal state, you see this linear in T behavior that can actually persist down to extremely low temperatures. Okay, so when people say that there's linear T resistivity in cuprates, and that's anomalous, this is really for me the most striking aspect of it, that it can really exist down to such low temperature. Moreover, it can exist over a whole range of doping. Okay, and in the same compound, in this particular cuprate, also the specific heat coefficient seems to be diverging logarithmically as a function of temperature. Okay, so this is really an unusual behavior. Doesn't this is sort of at least suggestive of a real non-Fermi liquid behavior. Okay, and one can ask, well, if this is some kind of non-Fermi liquid, what is the Lorenz ratio in this system? Okay, so we saw that at least within Boltzmann theory, the Wiedemann-Franz law is really tied to the existence of well-defined quasi-particles. So what's going on here? And that's been measured many times in many different compounds. And it looks like this is the Lorenz ratio as a function of doping in the same compound at the lowest temperatures. Okay, extrapolated to 0 temperature actually, and within error bars it's just 1. Okay, and it looks like in cuprates, in different compounds, different dopings, it's always pretty much 1 within error bars. And whenever people improve the measurements, it looks like it's just approaching 1. Okay, so it's measured both in the longitudinal and the transverse conductivities, and this is maybe the most dramatic example in the thallium cuprate. This ratio is 1 within 1 or 2%. Okay, so what does this actually tell us? What does that mean? Okay, on the normal state of the cuprates. Okay, does this mean that secretly the normal state of the cuprates is actually a Fermi liquid in disguise? Maybe there's some mechanism of scattering that we don't understand that causes the scattering rate to grow linearly with temperature, but underlying this is really just a Fermi liquid, or is it something else? Okay, so this is our puzzle. So in particular, what yeah.
The inverse solvability, most of the part of the case are forgotten.
Right, right. So yeah.
Say something about that, or not later, then maybe what are your thoughts on that?
Yeah. So that's true. So this is, if you like, this is another part of the puzzle. So that doesn't seem to go like the usual Fermi liquid behavior, and yet at the lowest temperatures, the Wiedemann-Franz law is obeyed. Okay, so how to reconcile these two facts? I mean, I think that's an open question. Yeah.
So if I go back to, trying to think of Wiedemann-Franz law in terms of Boltzmann pressure, if I write in terms of the variation of principle,
yeah,
you also maximize entropy, right? So
yes,
it
entropy
just
production.
follows from as I said, right, any solution Boltzmann equation with elastic, you have to get that.
Yeah.
So does it mean, is it obvious that, okay, I know that we shouldn't be using, we're told not to use Boltzmann equations if you don't have quasi-particles, but I
Right.
mean,
Yeah.
maybe
Yeah.
the variation of principle
Yeah.
of
This
maximizing entropy
this is basically
more general than just Boltzmann.
this is basically going to be my answer.
Oh,
Yeah.
sorry.
Yeah. Okay. But still, I'd like to point out there's something interesting that you might look at. But, yeah. Mhm.
You made the point just looking at the picture on the left, that there is a big difference between p equal to 0.24 and 22. If you look at the data that you showed, that says that the lowest temperatures.
Yeah.
If you look at the temperatures where you actually goes around Tc, 20, 30 Kelvin,
Yeah.
does Lorenz ratio goes down on these temperatures? In other words, you show that the data is the lowest temperature equals 1.
Yeah.
Is there any substantial deviation?
There is a substantial deviation in finite temperature. Yeah. I mean, this is really only the T goes to 0 limit.
So as I said, suppose that the T equal to 0 is it's elastic.
Yeah. Yeah. No. That's presumably what's going on here. Any interesting information is somehow in the finite temperature behavior, not
Right.
that the T goes to 0 behavior. On the other hand, you would say, well, you know, if it's a marginal Fermi liquid, if it's a non-Fermi liquid, then that should actually explain the T goes to 0 behavior as well, right? And then you would say, okay, so it just means that the Wiedemann-Franz law is much more general than Fermi liquid.
Right. On the other hand, looking at the blue pictures, which is few seconds.
Yeah.
Normally, you would say that elastic can be eliminated if temperature-dependent piece is larger than residual.
Yeah.
Which in this plot probably put you on a scale of about 40 and up.
Yeah. Yeah.
The question is, what is that?
Yeah. That's
when it comes down to
yeah.
it, it's not that.
Yeah.
You seem to make a huge assumption, which is that the carrier density is independent of temperature.
Right. So yeah. So
So
you know,
you're throwing out essentially
yeah. Yeah. No.
the
I
possibility that we're dealing with a Fermi liquid,
yeah.
making this huge assumption. What's the justification for that?
Yeah. I mean, this is basically why in this talk I'm focusing on the limit T goes to 0. So you know, at finite T, many things can happen.
Okay.
I claim that you know in this for this particular aspect, I really want to understand what's going on sort of as I approach T goes to 0. Yeah. Okay. All right. So what I'm going to do basically in the rest of the talk is just present a particular explicit model where I can do calculations, where I can just where I know that I get this a marginal or non-Fermi liquid behavior and just calculate the Lorenz ratio. Okay, so in particular, what I want to get is a marginal Fermi liquid. Okay, so there's this well-known phenomenological theory that has been proposed to explain the cuprates. Okay, and it's basically a behavior that gives you a logarithmic violation of Fermi liquid behavior. The real part of the electronic self-energy goes like omega log omega. And that by Kramers-Kronig means that the imaginary part of the self-energy, which is the scattering rate, goes like the maximum between temperature and frequency. Okay, and this, assuming that this is large angle scattering, immediately that the resistivity grows like temperature. It also means that the specific heat goes like T log T. Okay, now this is really an ansatz. It's not a theory. So just from this, I can't calculate anything. Okay, I actually need a model to do calculations. That's what I'm going to present. Okay, let me just point out an interesting fact. Okay, so in this model, okay, there's a coupling constant here in front of the linear in frequency or linear in T scattering rate. But if you really go to extremely low temperature or large lambda, and you calculate the electronic scattering rate, you have to divide the imaginary part of the self-energy by the frequency derivative of the real part, which is like z, the quasi-particle weight, and you get that lambda actually cancels. Okay, so you get that the actual scattering rate of an electron is T over log T. Okay, so it never exceeds T parametrically. So this sort of is a natural explanation of the so-called Planckian behavior that it looks like the scattering rate never exceeds something of order T in different materials. Okay, and the question is, what would be the Lorenz ratio of a marginal Fermi liquid? For that, we'll actually need a theory. We'll actually need an explicit model. Okay, so what do we do? Well, a Fermi liquid theory is not going to take us very far. It never gives this behavior. Okay, so we need to do something else, and that's what we'll do. Okay, so let me just take a short detour to try to motivate this approach to strongly correlated electronic systems. Okay, so we know what kind of models we want to be solving. Some kind of lattice model, some sort of, if you like, some sort of n-band Hubbard model with some number of active orbitals on every unit cell, and some complicated interactions between these electrons, some hopping matrix elements and some interactions, and maybe also phonons and disorder and so forth. Okay, so now we know that if the interactions are weak enough, we're just going to get Fermi liquid behavior. So that's no good. We don't want to use the interaction itself as our small parameter. What do we do instead? Okay, so what I propose to do is to use a different expansion parameter, which is the number of active orbitals per unit cell. Okay, so we do want to be able to control our calculations. We need some small parameter. So instead of the interaction strength, our small parameter would be 1 over n, where n is the number of orbitals per unit cell. Okay, so that limit obviously has its price. Okay, so to do calculations, that limit, we have to introduce a symmetry, either an exact symmetry or a statistical symmetry between the different orbitals. Okay, there's a large number of degrees of freedom on every site that can act as like a bath that can scatter the electrons. That's sort of an artifact. It's not something we expect in the real system. Okay, however, this type of approach can give us direct access theoretically to all sorts of non-perturbative, non-quasi-particle transport regimes that are very hard to access otherwise. Okay, so if you like, this is a possible way to map what are the possible behaviors of non-Fermi liquid without providing an actual realistic microscopic mechanism for any of them. Okay, so that's our approach. I'll just flash, yeah. Yeah, so n would be strictly infinity. If n is finite, there will be some crossover temperature where all the things that I'm going to show are going to disappear and will be replaced by different behavior. So yeah, so it's a serious issue. It's not just for convenience. The behavior I'm going to show actually does disappear when n is finite. Yeah. Okay, so just to flash some things that we did in the past with this type of approach. Okay, we looked at electron-phonon coupling. So here's an explicit model. We have n identical flavors of electrons, n bands, if you like, on every site, which are coupled to n squared Einstein phonon modes. And we're going to take n to be very large. So here's our Hamiltonian. Okay, we have n identical electron flavors and n squared phonon modes that we can organize in this matrix. Okay, A and B here are the flavor indices. J is the site index. Okay, and then we have two variants of this model. The phonons are either coupled to the electrons on the same site. Okay, it's this matrix in flavor space coupled to CA dagger CB, but it's all local on site. What we call that the Holstein type model, or the phonons are coupled to the bond density. Okay, so now this phonon displacement matrix XAB is living on the bond between site I and site J, and it's coupled to C dagger ICJ. Okay, so this is an SSH type coupling. Okay, and then yeah.
You answered that if n is finite, then this behavior disappears at low temperatures. But if you take n flavors and m phonons take both to infinity,
yeah,
make arbitrary ratio.
Yeah.
Does this theory still survive with extra parameter?
Yeah, yeah. So it does. Actually, in this particular theory, there's nothing wrong all the way to zero temperature. Also with the n and n squared. It's just that it gives you a Fermi liquid, possibly a superconductor at low temperature. Here we're for this particular aspect, we're interested at high temperature, where basically quasi-particles disappear. Okay, so we're interested in solving this model in a particular limit. Okay, so we have the dimensionless electron-phonon coupling that we want to be order 1. Okay, we don't want to expand in that, and we want to solve it for temperature which is much bigger than the phonon frequency. but still much smaller than the Fermi energy. Okay, and what happens in this model is that at some point, the mean free path of the electrons becomes of order of the lattice constant. Okay, so this is where Boltzmann transport basically breaks down, but we can still do calculations in this large n limit. Okay, this here are some results. Okay, so for the Holstein type model, this is the resistivity as a function of temperature for different values of the electron density. At very small temperature, it's linear in temperature. That's the usual Bloch-Gruneisen linear behavior for phonons. At high temperature, there's a crossover and it changes slope, but it still grows linearly with a temperature. Whereas in the SSH model, where the phonons are coupled to the bond density, there's a linear in T resistivity for low temperature, but when KFL becomes of order 1, basically when we approach the Mathieu-Ferreira limit, the resistivity saturates. Okay, so yeah.
How do you calculate transport?
Yeah, so we just use Kubo.
Okay.
So
and because of the large n, you don't need to report virtual fractions.
Yeah, right. And in fact, you can sort of understand what's the mechanism of this saturation and so forth at large temperatures. It's completely non-Boltzmann. The Boltzmann theory completely breaks down in this region. Okay, and but the large n limit sort of just captured that.
And the reason you get linear in T in the Holstein case, despite that they have finite phonon frequencies, what?
Yeah, this is all at temperature which is bigger than the phonon frequency. Okay, in fact, in these calculations, the phonon frequency is set to 0. Okay, but
temperature smaller than phonon frequency,
you would get
exponential.
Yes, exactly. Yeah. Okay, so nothing unusual there. It's really the high temperature which is sort of unusual. Okay, so so of course this resistivity saturation is something that's seen in many real materials, and this is what we were after. It's kind of interesting that it actually depends on the exact form of the electron-phonon coupling. Now, we wanted to see how serious is the fact that n is actually finite in real materials. Okay, so this model you can actually solve and calculate the resistivity even for finite n, as long as you take the phonon frequency to be strictly 0. Okay, then you can solve this model using Monte Carlo and calculate the resistivity explicitly. And this is what it actually does. Okay, so in dots here are the Monte Carlo calculations for finite values of n. So this is n equals 2, 4, 6, and 8. Okay, the 8 are these blue dots. And the solid line is the analytical solution for n goes to infinity. Okay, so yeah.
How are you calculating resistivity now for the Monte Carlo?
Yeah, so here it's important that omega naught is 0.
Oh, so then that proxy is exactly the same as actual resistivity, the one that we usually call?
No, so what happens is that then the phonons are completely static. Okay, so then you don't have any problem with analytic continuation. You can really just do everything. Yeah, once omega naught is non-zero, you're in trouble. It's much harder. But this we can really do with no extra assumptions. Okay, so it was very satisfying to see that at least qualitatively, even for n as small as 2 or 4, the qualitative behavior is actually captured correctly by the large n limit.
And the system does not generate your omega
dynamics. No.
It remains 0.
It remains 0. Yeah. Right. Okay, and there's some other predictions you can make from this model. So it was mentioned the whole density in this model actually would be temperature dependent in this resistivity saturation regime. Not quite the behavior we wanted, but for cuprates, but something else. Okay, so these are all things you can calculate. Okay, so then just in the last 10 minutes, I'd like to return to this question of what's the Lorenz ratio of a marginal Fermi liquid. Okay, and for that I'll need another model, but I'll also solve that model using large n. Okay, so we want to construct a model that would give us marginal Fermi liquid behavior, or more generally non-Fermi liquid behavior. And the building block we're going to use is the so-called SYK model. Okay, so this model basically of a quantum dot with n electronic orbitals, and they're interacting all to all by this quartic electron interaction. Yeah.
You're not going to calculate the Lorenz ratio for that model we're telling us about?
No, so that is all quasi-elastic scattering at high temperature.
Oh, so it's always going to be 1.
Yeah, it's just always 1. Yeah. Okay. All right. So So here's our model. We have each site would be this quantum dot with all-to-all interactions. For the single quantum dot, we know the solution to this model. It's actually an extremely interesting system. Okay, it has this anomalous behavior of the Green's function that goes like 1 over omega, very non-Fermi liquid behavior, all for a single dot. We know that it has good behavior in terms of self-averaging. The interaction here needs to be taken to be random in order to solve the model, and you only solve its properties, say the Green's function, average over realizations of this interaction, but it actually has a very good self-averaging property. So a given realization for large enough n basically behaves more or less like the average. Okay, it's maximally chaotic, which I won't talk about. And this offers a new window, if you like, into non-Fermi liquid behavior, and we're going to try to use that. Okay, so the first thing we'll need to do, since we are interested in transport, we can't look at the quantum dot. We need to look at a model that has some spatial structure. So we're going to construct a lattice model where each lattice point is occupied by one of these SYK dots. Okay, so we have n orbitals, n bands. And we want to be able to control the level of disorder in this model. So there's going to be some impurity scattering in addition to electron-electron scattering. So we want to start from a translationally invariant model and add disorder in a controlled way. Okay, and the way we're going to do that, the interaction is random, but it's the same on every site. Okay, so the model, it's not a Hamiltonian, it's an ensemble of Hamiltonians. But each member of that ensemble is actually exactly translationally invariant. And we still calculate properties average over realizations of this interaction. Okay, so here's our Hamiltonian. There's some kinetic energy, some hopping of the different electron flavors. It's actually all the same. They have exactly the same band dispersion. Here's the interaction that depends on I, J, K, and L, which are the flavor index, but it doesn't depend on position. Okay, it's the same at every site. And finally, we add also some amount of elastic disorder. This is just a random on-site potential that depends on both position and I and J. Okay, so that's one possible model. It turns out what we want is a slight variation of this model. This model can be solved. Its ground state is actually a Fermi liquid, so that's not quite what we want. Okay, there's a slight variation of this model, which is sort of inspired by heavy fermion physics. We have two types of electrons, each with n orbitals. We call them C and F, sort of making the connection with heavy fermions. Okay, and the idea is that their band dispersions are extremely different. So the C electrons are very dispersive. They have a very broad band. The F electrons are completely dispersionless. If you like, they're in a Mott insulator state. Okay, and so the two Hamiltonians are both of this form, but the epsilon K F of the F fermions is just 0. They just have a flat band. And there's a C to F interaction. Okay, so it's C dagger C times F dagger F, a local interaction, which is also translationally invariant. Okay, so that's our model, and we can solve that model in the large n limit. Okay, so as usual in these models, solving that model for n equals to infinity just reduces to solving a set of self-consistent equations for the self-energies. And once you have that, okay, so here the blue lines are the cold electrons, the red lines are the C electrons, the red lines are the F electrons. And once you have that, you can calculate any quantity you want, for instance, the conductivity just from Kubo. Okay, so, and it turns out that the solution of this model for n equals infinity is actually a marginal Fermi liquid for the C electrons. Okay, the F electrons have some different behavior, but it's the C electrons that are carrying the current. And it's basically the scattering of the C electrons from the F electrons is giving you a marginal Fermi liquid. It gives you essentially the same phenomenology as that proposed by Weizmann et al. Okay, so the DC resistivity is linear in temperature. And there's a whole variety of other properties you can actually calculate explicitly from this model. Okay, so then finally, we want to know what the Lorenz ratio of this model is. Okay, so we can calculate by the same method the thermal conductivity. And this is what it gives. Okay, so we know that in the clean limit, we take this disorder strength W to be equal to 0. we get that the electrical resistivity is linear in T. It turns out that the Lorenz ratio in the clean limit is it doesn't satisfy Wiedemann-Franz. It's constant as a function of temperature, but the value was not 1. Okay, so this is not a big surprise. This is actually also what it would do in a Fermi liquid. Okay, it turns out that for this particular model, it's some value, okay, close to 0.7. But this value is not universal. If you modify the model slightly, this value would change. Okay, however, now if you turn on elastic scattering, you get that the resistivity just satisfies Matheson's rule. So it's a constant plus a linear in temperature term. The Wiedemann-Franz law at t going to 0 is actually satisfied. Okay, so as you take t to 0, L over L naught actually approaches 1. Okay, but if you look at the first correction, and this was actually my student Ritau's idea, if you examine the first correction, it's actually linear in t. Okay, so there's some coefficient alpha, which is positive. It's not universal, but the deviation from Wiedemann-Franz is linear in t in this model. Okay, so and this is actually a sharp signature of a marginal Fermi liquid. Okay, so this is different from a Fermi liquid. In the Fermi liquid, it would go like 1 minus t squared. Okay, this is what it you could calculate this as a function of temperature. This is actually what it looks like. So this is the Lorenz ratio as a function of temperature. It approaches 1 linearly, decreases over a scale, which is basically the elastic scattering rate. And then it saturates when the temperature is much bigger than the elastic scattering rate, it saturates to this value of the clean system. Okay, and compare that to what happens, for instance, in silver. It kind of approaches 1 in a much more flat way. Okay, so we propose that this is what you should really look for. If you want the sharp signature, you should look at the behavior at low temperature and how it deviates from the Wiedemann-Franz law. Okay, so yeah, so that's basically my main message.
And if power at some point you get about power 3/2, it will be the same 1 minus
Yes,
IPT
yes,
3/2.
yes, exactly.
So it
Exactly.
follows the same power as this.
The same power, yes, yeah, you're right. So yeah, so what happens? Yeah, from Boltzmann theory, there's a very simple way to explain this. This is just a ratio between the electrical and the thermal resistivities. If one of them follows a different power from the other, or they have the same power but different coefficients, which would come if you have inelastic scattering at low temperature, then you would get this this deviation scaling like this, the stronger of the scattering rates. Okay, so what this requires is really that the scattering would be inelastic at finite temperature. The finite temperature contribution would be inelastic. So this won't happen for phonons above omega naught, for instance. Right, and yeah.
If you remember Achim Roche many years ago,
Yeah.
talking about linear in T as a small correction.
Yes.
Or not.
Yeah,
And in his case, it will be the same.
it would be the same. Yeah. It would be linear in T in 2 dimensions where he gets this correction to be linear in T to the resistivity. It's an elastic scattering. It enters differently in thermal and electrical. Yeah, it would be linear. Now, for us, it was just going back to this question: should we be surprised that at 0 temperature, a non-Fermi liquid satisfies Wiedemann-Franz? Depending on your point of view, I mean, I was somewhat surprised. You know, in these models, there is a Fermi surface, but there's no jump in the occupation function. There's nothing like a Fermi function as a function of momentum in this model, and yet it satisfies Wiedemann-Franz. Ultimately, I think there's a very simple reason for that. It's not a Fermi liquid, but it still satisfies a quantum Boltzmann equation. So that's actually much more general than Fermi liquid. And that's ultimately, I think, the reason. Okay, so you don't need to have a Fermi liquid. You do need to have something like a Fermi surface, which you do have in all these models. Okay, so we've done it for a marginal Fermi liquid. There's a slight variation of this model that gives you a strong non-Fermi liquid where the self-energy goes like some power law, which is smaller than 1. You get the same behavior. And you get 1 minus alpha t to some power. Okay, and that's it. I'm basically done. So this is my summary. The Wiedemann-Franz law and its violation can tell us something interesting about the mechanism of strange metals. I've discussed a clean metal near a Van Hove singularity where there's a very strong parametric violation of Wiedemann-Franz, and then a model of disordered marginal Fermi liquid. Wiedemann-Franz is actually obeyed, but the first correction actually gives us some non-trivial information about the mechanism. Okay, so yeah, thanks very much.
Thank you. Is it fair to say that this last line here is a consequence of absence of the FX correction? Yeah.
No, I don't think so. Yeah, let me just say this. We have an explicit modification of this model where there are vertex corrections. And this is still, this last line still holds. So it turns out this is not generally the case. So it's also important that you have that the interaction is completely on site. This is what for the connectivity, this is what makes the vertex corrections, the current vertex corrections vanish. Okay, and once you go away from that, you can just generalize the model slightly, make the in this case the C to F interaction a little bit, have some tail, which is not completely local. Then the vertex corrections and the connectivity don't vanish. Even in n equals infinity. Yeah. Okay, so you can still do the calculation and this still holds.
Well, to answer that question, but you have the data from Louis Pasteur. Does it hold there?
Yeah. In cuprates, I've never seen data that's really tracking this where the resistivity is linear, really tracking this down to very low temperature. I really hope that people. Yeah.
Which is that it's very low temperature.
Yeah.
The question was
What happens away? Yeah. So we sent this graph to Louis, and he pointed out that in Fermi liquids he does 1 minus t squared.
Okay.
He actually fits both the both the electrical and the thermal resistivities in this is a heavy fermion system. Both the thermal and the electrical resistivities goes as t squared, and he takes the ratio, and they don't cancel. So you get that the Lorenz ratio would be, the deviation would be t squared. Okay, so at least this is measurable.
Trying to calculate magnetic resistivity.
No, we haven't. Yeah.
Let me ask a question about the first part. Wonderful story about clean metal. Okay, going back to cuprates.
Yeah.
There's a lot of talks about Van Hove if the cuprates are around the same T equals
Yes,
0.24.
Yes.
So should we expect this behavior?
Yeah. It's just from Van Hove, it's not easy to get linear in T resistivity.
Right.
Yeah.
But I think for that one you don't need linear in T. For this square.
This is without linear in T resistivity. The resistivity is actually T squared log T.
Right.
But
do you expect then that cuprates near, if it's really Van Hove story, cuprates at P equals 0.24?
Yeah.
Then Lorenz ratio should go like that.
Yeah. So then
the
the question is if it is just Van Hove, where does the linear in T resistivity come from? Right. So it's kind of there's something at zeroth order that we're missing.
Right.
And the question is why is that? So that's also that's also true, right? I mean, so in the specific one I've shown, the Van Hove is really close by, but not in other cuprates, and yet right. So maybe this should show up, but I would sort of think this is a subleading thing. Here, the Van Hove for the thermal resistivity is giving you T to the 3/2, and it might be that whatever other mechanism is giving you linear T. So this is actually subleading.
Okay, more questions? If not, then thanks very much. Wonderful.
At one point, Max McKinsey wrote a paper about conductivity with optical conductivity.
Yes. Yeah.
It was the same story. Cold
Yes. Yeah.
We did something on top of it, but it was
Right.
his story.
Right.
So
It's
it
kind of
looks like very similar.
second order coupling to the magnetic fluctuations, and that you can have anywhere on the Fermi surface.
Right,
Yes.
exactly.
Yes.
It looks similar to.
Looks similar. Yeah. So this is I mean same words. Go along. Yeah.
I take it you have not yet had lunch.
I have not had lunch. Yeah.
So,
We arranged that he didn't have lunch before.
okay, yeah, I noticed. So you must be really hungry now, no?
Not yet. I'm still on the
Shall I-
adrenaline, but I'll be hungry soon. Yeah.
If you want to chat a little bit more, shall I find you here in 5 or 10 minutes? Or
Sure. Yeah.
You want to keep your stuff in my office, which is in this building?
Sure.
upstairs
Sure.
afterwards?
Yeah. We can do that. So
I'll be back shortly.
yeah.
Good.
All right.
Natasha.
Hey.
Very stupid question, forgive me in advance. So you consider an array of FYK tops,
Yeah.
but you don't include any hopping between different tops, right?
Right. So there's no hopping. There are two types of electrons, C and F. There's only hopping between the C's. No hopping between the F's.
But if you don't
Exactly, for just 1 second. I'll disappear and then will
Yeah.
reappear again.
Right. Okay. Yeah. Great.
Yeah. Well, I'll check. But
Okay,
I mean, I
between the
don't
dots,
write
how do you get the corresponding band structure?
You know what?
Yeah. So the C electrons do have hopping. Yeah. So
And the interact electrons too?
yeah.
I see. The second time I'm listening to your talk, and the second time I don't. Thank you so much.
Yeah.
Thank you.
Right. Because the other thing you could do is, but I've already told the instructors, this thing of the drop, you can offer, if it's something C, there's C, or is it F, you can say, do you want to drop or do you want to make up? You can just not do a make up. I mean, this thing of like not giving a makeup and causing all this trouble, is it worth it? Or you can replace the files. They're all awesome, but they can't tell her.